explains the physics behind all sorts of things we see in everyday life. So the title is The Physics Behind and it's got all sorts of questions for us that it's going to answer, like what makes films 3D, and it's got a pair of 3D glasses here. Find out why your high-speed Wi-Fi is worse than your friend's. How fingerprint recognition works. Understand what is really driving your brand new driverless car. How the ice cream and the beer diet works. What happens in a nuclear meltdown. And then we've got this spiral that explains time travel. Here it reads, discover the physics of everyday events. And then at the back, we have find out why north is really south. I've read about this one. Discover how face recognition works. The science behind a bag of sugar. And much more. Discover more about the science that makes the world go around, including everyday technology, objects in the home, amazing physics in nature, incredible engineering, and the science behind things you would never have thought of before, such as electric guitars, executive toys, and wristwatchers. Packed with detailed illustrations, the physics behind is perfect for everyone who has ever been curious about the science of life. Okay, so let's open up this book and see what it is about. On the first page, we've got this bold blue background. Oh, it sounds awesome. And then we've got the title again, The Physics Behind, with the 3 little dots. Then we've got, again, the same title with the 3D glasses and a little bird here. And then we've got fun little illustrations. Here's the atom. Magnets. This is the nucleus of something, probably chemical element, I'm not sure. DNA, the light bulb, telescopes. No, sorry, antennas, not telescopes. And little flasks. Okay. It was published in 2018 in the UK. So let's take a look at the contents here. 6, we've got the introduction, the physics behind modern life. 10, on page 10 we've got Wi-Fi. Page 14, facial recognition. 16, touch screens. 18, microwave ovens. 20, ice cream and beer diet. 22, taking a selfie. 24, flash memory. 26, a pack of sugar. on to analysis. 52. Medical imaging. 56. Looking at little things. 58. Spectroscopy. 60. Crime scene investigation. 62. Tricorder. 64. Microfluidics. 66. Radiocarbon dating. 68. Proving the Earth is round. Then we have space. 74. Is it really rocket science? 78. Space weather. 80. Planet 9. 82. Space telescopes. 86. Is there anybody out there? 90. Life on Earth. 92. Life on Mars. Then we've got big science. 96. What's the matter? 98. Time travel. 100. Bomb or meltdown. 102. The Large Hadron Collider. 104. The Human Genome Project. 106. The Standard Model. 108. Gravity. 111. Everything. Then we've got Weird Universe. Page 116. Strings, rings, and other things. 118. N-dimensional space. 120. The hypercube. 122. Antimatter. 124. The dark universe. 126. Quantum weirdness. 128. Quantum biology. 130. Time crystals and Majorana. I'm not sure I pronounced that correctly. The environment. 134. Weather forecasts. 138. Climate change. 140. Renewable energy. 144. Migration. 146. Peacock feathers. 148. Sunburn. 150. Rainbows. 152. Spider silk. Then let's move on to transportation. 156. Autonomous autos. 158. Hyperloop. 160. maglev. 162. Satellite navigation. 164. Motorsport. 166. Going really fast. 170. Stealth. Then we've got everything else. 174. Curveballs. 176. The Mamba effect. 178. Why north is really south. 180. Perpetual motion and the heat death of the universe. 182. This book. On page 184 we have the rest, which is in-text, picture credits, and acknowledgements. So, okay, now let's read a few things in the introduction. Life today is underpinned by its scientific discoveries in ways that are not always appreciated. We take for granted that food can be eaten in a few seconds, that aircraft will arrive at their destinations, that our newsfeed will be delivered to our pocketable device, and that we can upload an image with a casual tap of a finger. None of this would be possible without amazing breakthroughs in physics. In just 4 or 5 centuries, our understanding of the mechanism of the universe have moved from superstitions and sorcery to our present relatively enlightened position. Humans have done this by being inquisitive inquisitive, logical, and sometimes a bit eccentric. Actually, quite often a bit eccentric. It is in our nature to ask questions, to wonder how and why things work, to peek under the hood and mess about to see what happens. This is a quality that must be encouraged, our collective tendency to mess with the things that has brought us great advances in science, engineering, as well as the arts and humanities. It has also led us to do substantial damage to our home world while giving us the insight to start putting things right. This book gives a peek under the hood of the physics behind a range of everything phenomena, from the devices we all rely on to some of the more exotic stuff happening in the wider universe. Rather than simply looking at what happens, we see how and why it happens. We start with modern life, where a commonplace technology is explored to see what makes it tick. Even mundane activities such as catching a train or weighing a bag of sugar involve some quite surprising phenomena. And have you ever wondered what really happens when you take a selfie? Life would be dull without entertainment. And in this section we reveal the unexpected physics behind some of the ways we amuse ourselves. Why is a Blu-ray disc misnamed, and why was its diameter the result of something of 200 years ago? Everybody has some medical test from time to time, but we rarely stop to consider what the analysis of our sample is carried out. How? The physics behind laboratory instruments and some of the technologies arriving soon may surprise you. Rocket science used to be quite easy to understand, but recent developments in space are changing the very basics of exploration. Is there life elsewhere? What can physics tell us about the prospects for biology on Mars? No questions are bigger than the questions posed by big science. We live in an age of unprecedented scientific discovery, where the biggest and smallest things in the universe are being probed in ways never before attempted. Some of the answers seem so unlikely that they have a section on all their own. Weird universe. Back on Earth, we explore some of the physics behind the environment of our planet, including unexpected phenomena in the natural world and the realities of what human activity is doing. I think this must be a typo. It's not word, it should be world. Transportation is changing faster than many other technologies. Here we explore the physics behind driverless cars, speed trackers, and stealth. Everything else looks at a few oddities, including why every magnetic compass in the world is wrong, and what is really going on when you read this book. In all this, we've tried to reflect the most up-to-date knowledge available. Knowledge changes, and scientific fact is sometimes just this year's best guess. Let's peek under the hood together and explore the physics behind. By Rose Swan. Here we've got a yellow page with some fun little illustrations. Again, we've got the microwave, the ice cream, a compass, the stars. We've got a radio over here. So let's read about Wi-Fi. If you ever feel like your Wi-Fi connection has disappeared into a black hole, you might take some comfort from knowing that technology only came into existence because of a failed physics experiment to build Wi-Fi is everywhere these days, with billions of devices including laptops, televisions, mobile phones, and security cameras, all using it to connect to each other and the wider internet. In essence, it sends and receives digital data by radio communication between a device and a base station such as your home internet router. If you want to be really accurate, it uses parts of the electromagnetic spectrum in the microwave region, which are shorter and higher frequency than radio waves. Getting digital information across relatively short distances with low-power devices might seem to have little in common with radio astronomy, which uses huge receiver dishes to peer into the far reaches of the universe. It might seem to have even less to do with a Hollywood actress or a way to steer torpedoes, but the world of physics is full of surprises. Austrian-born actor Hedy Lamarr fled to the USA shortly before the beginning of the Second World War and became one of the Hollywood's biggest stars of the 1940s and 50s. She was also an inventor, and in 1942 was granted a patent along with the composer George Antheil for a way to prevent signals of radio-guided torpedoes being jammed. Her idea of frequency hopping was not properly recognized at the time, but later became an important feature of many wireless technologies, including both Wi-Fi and Bluetooth. 30 years later, physicist Stephen Hawking came up with the then astonishing theory that black holes might not be completely black but actually emit some radiation. This should, in theory, allow them to be detected. Among those trying to find this predicted Hawking radiation was electrical engineer John O'Sullivan, who reasoned that all that was needed was to make radio telescope images sharper and more sensitive. His idea involved using Fourier optics. See the deconstructive accord panel on page 12, and would have been brilliant if it had worked. It didn't, and black holes remain invisible to this day, but the work did lead to patents for wireless networking and now ubiquitous Wi-Fi. Patent controversy. Major patents for Wi-Fi technology were granted to CSIRO, pronounced Zyro. But with the huge commercial success of the technology, there were many rival claims. In several U.S. court cases, the Australians' patents were upheld, and Dr. Sullivan claimed to be the inventor of Wi-Fi reinforced. The main patents expired in 2013 after earning hundreds of millions of dollars, but all those court cases mean that lawyers probably made more. The Multipath Problem. A clean Wi-Fi signal has to overcome the problem of multipath interference, where the signal arrives at a device by many routers directly from another device or reflected from walls, ceilings, and any other nearby reflective surface. Because of the way waves can combine or subtract from each other, a multipath problem could make practical Wi-Fi almost impossible, were if not for a couple of tricks. First is Lamarr's frequency hopping technique, which splits the signal across different wavelengths that each reflect differently. Second is the inbuilt error checking wireless devices such as a checksum calculation to reveal whether the information received is the same as that sent. What is checksum? Let's say that data being transmitted was the physics behind. If we give each of the letters and spaces a numerical value, A is 1, B is 2, and so on, with 17 for a space, we can transmit the word many characters had been sent. This would show if any had been lost or gained, but not whether any had been corrupted. You wouldn't know whether the phrase was the physics behind or the moon is cheese, because both are 18 characters long. A simple checksum might be to add the numerical values of the letters 20 plus 8 plus 5 and so on to get 228. The receiving station does the same calculation and checks whether it gets the same answer. If it does, there is a good chance the data had been transmitted successfully. If not, there is definitely an error and the whole string can be sent again. Real-life checksums are more complicated but follow this basic principle. Deconstructing a chord. The field black hole detector that we discussed on page 10 was an attempt to distinguish feeble Hawking radiation from all the other radio noise in the cosmos picked up by radio telescopes such as Jordal Bank in the UK. The resulting jumble of wavelengths is a bit like a musical chord where many different notes are played at the same time. The trick here is called Fourier transform, which is able to deconstruct a complex wave into several simple waves. It's a bit like hearing a C major chord on a piano and working out that it must be composed of the individual notes C, E, and G. French mathematician and physicist Joseph Fourier came up with the process in the 1820s, about the same time as he discovered the greenhouse effect of the Earth's atmosphere. Why is it called 802.11? The term Wi-Fi has become universal and refers to devices based on standards known as IEEE 802.11. IEEE is the Institute of Electrical and Electronics Engineers, a US-based professional association that has been operating since the 1960s. It has a number of committees, and wireless networking just happened to be the 11th standard agreed by committee number 802. Additional letters 802.11ab and so on are simply the various specifications of wireless networks. The 802.11 standards are in continental state of development and improvement driven by the need to transmit more data more quickly and with greater security. Each new standard is marked by an alphabetical suffix, so 802.11g is lower than 802.11n. When about half of the alphabet had been used up, the designation changed to two letters, 802.11ac, 802.11ah, and so on. There is an old joke that a camel is a racehorse designed by a committee, and the confusing list of wireless standards might be evidence that these were thrashed out by a series of committees. To be fair though, technology has improved rapidly in the late 20th and 21st centuries, and nobody could have foreseen how this would drive the demand for better, faster Wi-Fi. Ever faster standards. The first 802.11 standard now looks rather quaint, and with its missile 1 or 2 megabits per second streaming capacity. Think 5.5 hours to stream a DVD. That's about 3 times as long as the movie itself. To add to the confusion, the A and B standards were compiled at the same time, and it is sometimes thought that B came before A. This isn't quite true, but certainly 802.11a immediately demonstrated faster speeds as a direct result of using higher radio frequency 5 GHz instead of 2.4 GHz. This created a new problem of its own because the 2.4 GHz band was already popular and was being developed for future standards. The higher frequency offered more bandwidth but poor compatibility. This problem is solved on later standards by using both 2.4 GHz and 5 GHz frequencies, allowing Wi-Fi networks from 802.11g onward to be compatible with most existing hardware. It's one thing to be able to stream content around the house at high speed, but the convenience is reduced if you have to replace the network card in your laptop and connect the TV, and if your current smartphone can't talk to your router. The latest standards bring even more speed and promise to maintain backward compatibility. Available from 2019, 802.11ax transmits at over 10 Gbps. What is that? Megabytes per second. Oh, gigabytes per second, which is fast enough to download that DVD in just 4 seconds. Let's read about facial recognition. The smartphone is truly the wonder of our age, combining the power of a computer and the entertainment system, camera, and sensors to enable it to be anything from a spirit lever to a video broadcasting station. With all the value and personal data locked up in a small slab of glass, and electronics is becoming more and more important to keep the bad guys out. This need will only increase as it becomes routine to use a phone as a wallet, paying for items in a store with a simple wave. One recent development that has rival phone makers trying to outdo each other is biometric identification, a big phrase which simply means checking that the person using the device actually is the owner. Biometrics are also used in passport control and other security applications and seem certain to increase in future. Biometric ID. While a password or a code relies on something you know, a biometric identifier relies on something you are, and so you should be harder to crack. That's the theory anyway. Lots of different metrics have been tried with varying success. Fingerprint recognition is common but may not be that difficult to hack. Iris scans, earlobe shape, voice ID, and even pose have been put forward, tried, and all can be made to work, but may not be convenient enough for everyday use. Trust his face. In 2017, Apple introduced a new facial recognition system called True Depth, which uses an array of cameras, lights, both sources, and sensors to create a 3D model of the owner's face and then compare this to anybody trying to unlock it. The challenge of 3D is that it's really difficult to do with a single camera. But if facial recognition is only 2D, it might be spoofed by something as simple as a photograph. True Depth cracks the problem by exploiting the properties of infrared light with the huge computing power now available in phones. An infrared projector sprays a pattern of over 30,000 dots onto the face. When setting the phone up, a user must look at the screen and turn their head in a complete circle. The position of the dots is recorded by an infrared camera position just about as far away from the projector as possible. Their apparent movement gives the depth perception needed. This information is processed by an onboard neutral computer that can apparently perform 600 billion calculations per second. That's about the same processing power as the best supercomputers in the world, and at the turn of the century, in your pocket. Here we've got the first figure with the little dots that they talked about in that paragraph. True depth face recognition fires thousands of points of infrared light onto a face to check whether it matches the phone's owner. The learning machine. The importance of the neutral computer approach is that this enables machine learning in ways similar to a human brain. The neutral processor used for true depth should be able to tell if the person using the phone is you, regardless of whether you're wearing a hat, glasses, scarf, or are growing a beard. Neutral processing is key to the most promising attempts at artificial intelligence. Not everybody welcomes the growing presence of biometrics, but as the technology improves and becomes cheaper, it seems certain that this will be a routine aspect of daily life in the future. One day we may expect to see DNA recognition as the ultimate in biosecurity, and it is certain that every increase in security is accompanied by a parallel improvement in the sophisticated and cunning of would-be hackers. Okay, let's read a few things about touchscreens. The touchscreen has become the almost ubiquitous interface between human and machine in just a few years. It can sometimes be a surprise to discover that a screen is not touch sensitive but merely an information display. Touchscreens aren't all the same, and the technologies they use each exploit different physical phenomena. Resistive touchscreens, the variable electrical resistivity of a sandwich of materials when subjected to pressure, was the trick behind early resistive touchscreens. That's a word I struggle to pronounce. That and strategy. Two conductive polymer layers are separated by a small air gap, and each layer is edged with a series of tiny parallel wires, on one layer going up and down, on the other left and right. A small voltage is applied to the layers, but the electrical circuit is incomplete because of the air gap. Incomplete, that is, until little pressure is applied to the top surface, causing it to deform and allowing the two layers to touch. The edged conductive lines reveal the XY coordinates of the point of contact and tell the software what function you are asking for. Resistive screens are considered a little crude nowadays. They can't really cope with multi-touch functions as the pitching and zooming, but they do have the advantage that they can be operated with a stylus or gloved hand. Capacitive touchscreens. More modern screens found on smartphones and tablets use a different electrical trick. These capacitive touchscreens are generally made of glass, which is more scratch resistant than plastic, topped with conductive materials to hold a tiny electrostatic charge. This is the same type of charge you can get by rubbing a balloon on a woolly sweater or walking over synthetic carpet, only much smaller. There are two slightly different ways that bottom surfaces of the glass. When the top surface is touched by an electrical conductor such as your finger, even very lightly, the capacitance of the material changes at that point. Capacitance is the ability of an object to store electrical charge. Making contact with the object causes the electrostatic field to change at that point. Sensors around the edge of the screen detect the position and can cope with several points of contact simultaneously. Touchscreens are the essential link to today's portable technology revolution, putting an incredible connected supercomputer in everybody's pocket so we can look at pictures of cats. Then first on figure 1, we have the resistive touchscreen that has, that resistance I talked about. When you touch the screen, the two layers meet, completing the electrical circuit. Then here on figure 2, we have the capacitive touchscreen. Your finger acts as an electrical conductor, changing the electrostatic field of the surface where you touch it. On figure 3, we have the total internal reflection. It's got an LED here, acrylic paint, scattered light. Let's read about next generation touch. More precisions and an even lighter touch is promised by a new generation of touchscreens which exploit a property of light known as total internal reflection, which is this one, I'm guessing. This occurs when a beam of light is traveling toward a less dense medium, some from glass to air for instance, at an angle greater than the critical angle for that material. On reaching the surface, it is completely reflected back onto the dense medium. When an object approaches close to the surface, this total internal reflection is frustrated and some of the light is scattered instead of being reflected. This scattered light can be picked up by sensors on a far surface to reveal the location. Frustrated total internal